Okay, so welcome back to forward and inverse kinematics. What we're going to be doing is now finding the inverse kinematics of this arm that we just found the forward kinematics vector for using DH notation. So you can go ahead and watch the previous video, part 1 of this, in order to figure out how we got the forward kinematics. But now, in order to get the inverse kinematics, what you have to do is it's actually relatively difficult. It's more of an art than anything else because in all the other parts of robotics up to this point, you have a very set kind of rules and procedures that you follow through in order to solve a problem. But in finding the inverse kinematics from the forward kinematics, you have to really be able to see the patterns and know how to solve something. So looking at this, the first thing I'm going to do is I have this little chunk of stuff right here that makes it kind of complicated to work with the equation. So I'm going to simplify that down to A. So I'm going to start off by making A, oops, not Q, A equal to sine of Q2 of 1 plus Q3 minus 1. So that's going to simplify my equations a little bit. Alright, so now looking at this, these set of equations again, there's one rule that is actually kind of handy when you're working with this stuff, and it's x squared plus y squared is equal to 1, basically. That's the simple thing. Let me find the correct equation here so I don't tell you a falsehood and get you confused before I go right into this and start showing it off. Okay, x squared plus y squared. Yes. Oh no, it's not the rule of x squared plus y squared. In fact, it's sine squared plus cosine squared is equal to 1. That's the one I'm thinking. But you end up with an x squared plus y squared in just a minute when I'm showing this to you. So, what we want to do is we have a lot of sines and cosines running around up here, as you can see. So what I want to do is I want to get this stuff simplified. So I'm going to take these parts of the vector right here and set them equal to x and y, so I get it quick and easy and in an equation form. So I'm going to have x is equal to negative 2 sine of q1 plus cosine of a, and then y is going to equal 1 plus 2 cosine of 1 plus sine 1 of a. Cosine 1 of a. So now I've got my two equations here with the a taken out, so it's all clean and easy. But now that you can see, if I do one more step here, y minus 1 is equal to 2 cosine of 1 plus sine 1 of a. Now if you compare these two equations, well, we both have a cosine, we both have a sine, and they're in inverse locations to each other. So if I do an x squared, y squared, I'll end up with a sine squared plus cosine squared in each one of these equations. And that'll allow me to cancel a bunch of stuff. So going ahead and doing that, taking the square of both of these, x squared is equal to 4 sine 1 squared plus a squared cosine 1 squared minus 4a sine 1 cosine 1. And then taking the square root of this over here, I'll end up with y minus 1 squared. We don't have to expand that out. Is equal to 4 cosine 1 squared plus a squared sine 1 squared plus 4a sine 1 cosine 1. So expanding all that stuff out and doing all the multiplication of these two equations. That'll get us to that step. Now, if we do x squared plus y squared, which is what I was talking about before, you will end up with x squared plus y minus 1 squared is equal to 4 plus a squared plus 4 sine 1 cosine 1 a minus 4 sine 1 cosine 1 of a. Now you may notice I kind of skipped some steps there, but what happened was when you add these two together, if we just imagine these not as equal to each other or added to each other, you've got a 4 sine 1 squared and a 4 cosine 1 squared right here. Well, sine 1 squared and cosine squared, if you factor out a 4, you'll get 4 of sine 1 squared plus cosine 1 squared and these cancel the 1. So that's where the 4 comes from, right here. And then you do the same thing again with the a squared over here, so you just end up with a squared, and then you just add these two together right here. And that's where that equation comes from. So we actually just got rid of a whole bunch of nasty trig functions that we don't really need. And then these actually cancel themselves out, quick and easy. So we've got x squared plus y minus 1 squared. And we'll move the 4 over to the other side, is equal to a squared. So then, going on with that a little further, if I take the square root of both sides, and then I put in a's actual value, so a is equal to s2 of 1 plus q3 minus 1 equal to the square root of x squared plus y minus 1 squared minus 4, just like that. So plugging in the value of a. And then simplifying this out a little bit more, I'm able to get s2 is equal to the square root of x2 plus y minus 1 squared minus 4 plus 1, because I add this 1 on the other side, and then divided by 1 plus q3. And now I have q2 almost defined. I still have this sign. I really don't want to take the inverse sign of this whole side because that would not really be complete. A complete answer has almost no trig functions in it at all, ideally. So we've got a basic thing right here, something we can work with because we've got q2 defined as just the sign of something. So that's something we can work with. So now, using 3 and 4 of the this thing up here, so 1, 2, 3, z and 4, so q1 and that, z is equal to 4 plus cosine of 2 of 1 plus q3. Alrighty then. Splitting that up a little bit, we end up with c2 is equal to z minus 4 all over 1 plus q3. Alrighty. Oh, actually, we're not using 3 and 4. I'm sorry. We're just using 3 in this part. The 4 comes a little bit later, or in another method. But using c, now we have cosine of q2 and sine of q2. Well, it would be really easy to just define these now by taking and dividing them by each other. So if you were to take the q2, oops, sorry, q2 is equal to a tan 2. I'm actually going to skip a few steps again. Square root of x squared plus y minus 1 squared minus 4. I don't really skip a step, but you'll be able to see where it happens in just a second. Okay, so right here, this could be equal to tangent of negative 1 of the cosine of 2 over cosine of 2. So if you look at the sine 2 over cosine of 2, you'll have this over this. So the q1 plus 3 will cancel, and you'll end up with z minus 1 on the denominator and this in the numerator. So you can look at this as the denom, and this is the numerator. So now you have something that you can actually solve. We have q2 completely defined. That's it, which is a huge step in the right direction. So right there is an answer you can almost use. You of course want to simplify that a little bit, because if q2 is equal, going through here and again simplifying all these kind of things and moving out and around, you'll find that q2 is equal to theta wherever q3 is equal to negative 1. Because right here, if q3 is equal to negative 1, then this all falls apart because it all goes to 0. So q3 equal to negative 1. But either way, we still have q2 completely defined. Okay, so that's how you get the q2 value. And you can see that since q2 is not in relation to another q anywhere, you have it completely solved, and it's something that you can use in future equations, which I'm just about to show. So I'm going to go ahead and solve for q3 right now because it's pretty easy. So for q3, The equation I'm going to use is this one, is equal to z, and I've got it written right here. So now if you take this and you solve the z equation with respect to Q3, you end up with this. And that's your complete answer. That's all you have to do. You don't have to do any fancy manipulation with this one, like squaring anything, in order to get the complete answer. Now you may notice that we have a Q2 down in this one, but that's alright, because since Q2 is basically a constant up here because it doesn't have any Q's in its values, Q3 can be defined with respect to Q2, and that's alright. But Q2 can't ever be pi over 2, otherwise you get an undefined equation in here because this will equal 0. So you don't want to do that because it will make the whole equation undefined. So those are just two areas to avoid. That's a condition you put on the side there if you want to. Alrighty, so that's Q2 and Q3. Now solving for Q1, what I'm going to do is I'm going to go back to these two equations up here that we defined earlier using A and the first two parts of the matrix in the forward kinematic table, or forward kinematic vector. So I've got negative 2 S1 plus A C1 is equal to X. Then I've got A S1 plus 2 C1 is equal to Y minus 1. Okay. Now you may notice that we have a pretty nifty little lineup like this because it's all formed so that it can actually be turned into a matrix, which we're going to do right here. So we're going to go ahead and do minus 2 A 2. So these first two parts of this matrix right here. And then sine 1 cosine 1 is equal to x over y minus 1. Alright, so there's nothing we can really do right there, so we're going to go ahead and solve for S1 and C1 because we're trying to find Q1. So in order to get those, you go ahead and take the determinant 4 of a squared, which is 2 squared minus a squared. 2 times 2 minus negative a times negative a. Times 2 negative a times 2, which is the inverse matrix, inverse negative matrix, times x of y minus 1. So, and again you have a equal to sine squared 1 plus q3 minus 1 up there at the top right here. So remember that. If you go through and you solve all this stuff out and you do all the math on that, you'll end up with q1 equal to a tan to the arctangent of S1 over C1. Which in this case would basically be Q1 is equal to itself. But that's a little bit incomplete because S of Q1 can change and vary a little bit, but Q1 will basically always equal itself. But this is the equation that you want to define as the final answer in this case. And just use your favorite equation solver like MATLAB or Mathematica to get this part of it. Alrighty. So then, in order to define Q4 is another easy one because looking at the forward kinematic matrix, oh look at that. Q4 is just equal to psi. So Q4 is equal to psi, like that. And then I did Q1, Q2, Q3, and that's it. So, yep, that's the entire problem. Make sure I didn't miss any comments anywhere that I need to tell you. Nope, I think that's it. As you can look at this forward kinematic table and you'll ask why Q1, or no, Q2 wasn't equal to theta right off the bat. That's because Q2 only equals theta. Let me grab the right chunk of paper here. Q2 is equal to theta, alright, but only when Q3 is equal to negative 1. So that's a special condition right there. Otherwise, Q2 is equal to all this mess. So that's the reason Q2 couldn't be like Q4 and just equal psi directly. Q4 is defined only by psi and isn't included anywhere else in the equations, so it doesn't need any of the special conditions. And that's the inverse kinematics from a forward kinematic table. Hopefully it helps you a little bit.